So far we said this was f of x. And then we said that g of x is going to be the integral of f of x. And then we made this big connection and we wrote this down on our paper. The other stuff would have been typed out. We made this connection so we could talk about it. The question is it speeding up? So g prime of x is greater than 0 means that we're going forward. This means we're going forward, yes? We're going forward. But that's not the question. The question is, are we speeding up? When so from, let's give it some intervals. Okay, so we'll call this 2. From 0 to 2, g prime of x is increasing. There's some calculus for us. So that means we were going forward and our slope is increasing. So we're speeding up here. Okay, what else? Okay, so not quite. So, okay, you're in your car, you're at 0, you're in the parking space, you back out, and then from 0 to where you stop backing out, like you are going faster, and then you stop again. So when are you going faster? Okay, you are. This is velocity. You're in reverse direction. All of this, you're moving forward. All of this, you're moving backward. This is when you're standing still. Okay? Does that help? So you're still here, forward, backward. When are you speeding up? In reverse. From 3 to floor. Not 4. Floor, but 4. From 3 to 4. Because g prime of x is less than 0 and g prime of x is decreasing. Oops, decreasing. So you have to be doing the same thing, okay? This is positive and this is positive. The second derivative, this is g double prime of x. That's supposed to be 2 little tick marks. It's really bad. Is also greater than 0. They have to be the same sign. If you're going forward, you have to be accelerating. So this is also bigger than 0. And then if you're going in reverse, so this is reverse, you have to be below the x-axis and you have to be decreasing. So you sped up to here and then you're going back to 0. See how this part is not speeding up? This is where you sped up from 0 to going fast and then you went back to 0 and then changed it forward again. So speeding up has the same sign for velocity and the second derivative. Slowing down has opposite signs. So when I asked you to think about this over the weekend, that's what I need for you to like picture as you're driving. Because if you start to see, okay, I'm stopped at a stoplight, my velocity graph is 0, I'm speeding up. Like if you start to see it as you move around, you're like applying calculus all the time. And these things will come to you like the multiplication tables. That's what I want. I want it to just be like natural. So I'm forcing you just a little bit to think about it, and the direction is obviously important. Getting this part, you know that. Like if I asked you about it, you'd probably figure out that this is velocity, velocity equal to 0 at these points, but in actual use of it, it may not come to you so quickly. So it's good to revisit this, even though this was like our very first class from our homework assignment over the summer work. I still want you to make those connections. So does that help a little bit? Okay, because speeding up is actually a question, because speed is the absolute value of velocity. So you have to consider both the positive and negative versions of it. There's 2 choices there. Okay, so we got there? We have 2 more sections in this chapter, so that was sort of an aside. Here's where we are. Today we're going to do natural log integration, which is great, not difficult. After you've got U sub, after that things look pretty easy. Tomorrow we're going to start some FRQ practice. So I've got 3 FRQs that are different kind of problems, but they're very short. They're not like 4 sections of problem. So we're going to look at those together. And then I've got some AP videos for homework to lead into our last section of this chapter, which is inverse trig. And we're going to use complete the square here. I've seen this on at least 2, I think, of the tests that I've given, which is not that many. So, well, I don't give them, but Mr. Wang does. So we definitely want to have a clue about this section. So AP video for homework and no math to do. Just watch the videos and take notes. Then we'll look at this together. We're going to go over that homework, and then we've got a circuit to go through on Thursday. That will be what you have for the weekend. Then next week will be in March. So in March, we're going to go over the circuit from the weekend. We're going to start a review circuit. So you have several days to do it. So we'll be doing that this week. That gives you plenty of time to do all of the different problems and think about what they might be. And if you get stuck, ask questions. And ask me questions through here, because I don't have a day of just questions before your test, which is going to be a week from Thursday. Okay? And it's on the calendar, so it should show up on your Google Calendar if you're looking. So on this test will be, we did U substitution. We're going to do natural log integration, except it's not going to look like that at all. And then we're going to do inverse trig. So there'll be real math, and then there'll be probably an FRQ, because we're spending some time on FRQs. That's where we're going. 4.6. All right, so this is called natural log integration in your book, but there's also an aspect of long division here, so I want to include that in the title. So if you're going back to look at stuff and you're like, wait a minute, when did we do long division? You can spot it. So the log rule for integration looks like this. You already know that if we said d dx of natural log of x, that would be 1 over x. If we had something more interesting, so we have the natural log of x squared, then we would say 1 over x squared times 2x. So we'd chain rule it, and then that would simplify. So that ring bells to you. So I'm not going to simplify it for a minute, because I really want to show you our sort of rule that we're working on today, which is the integral of 1 over u. Well, am I going that far? This will be the short one. Du equals the natural log of the absolute value of u plus c. Don't forget that plus c, k. Not k, but c. Sorry. Because y'all, some of you are forgetting it on tests, and it's easy to do. So when you go into any test, think, okay, plus c, that's the bane of Miss Tate's existence. It might be the bane of mine. It's a couple points, but don't forget it. And there were multiple choice that had plus c on there. When you see those in the test, circle them real big and go, oh, did I do that somewhere else? Okay, and you'll find them on the AP test, and you can add them to your notes or the front page or whatever, so you don't forget. Okay, that's the general version. Here's the most interesting one, though. We've got u prime over u du. That's going to be the natural log of u, absolute value of u, plus c, when we've got chain rule happening. So this one up here could have just been plain x, I guess, to make them more simple. But if this u is just a nothing with a derivative, then we're going to go natural log. We're taking whatever the argument was, and we're putting it into the absolute value. And the reason for that is what? Why do we need absolute value? Well, it has less, well, it kind of has something to do with this. I mean, for example, 1 over x, if you look at that graph, what does it look like? So it does come from this. That's that crazy one, right? That goes like so, like this, right? So what does this graph look like? Do you have anything over here in the less than 0 category? No. So you have to put absolute value because there is no, you can't, even though this has a lot of x values or whatever, I don't have a function here, but probably does, this one does not. So you can't, usually the integral takes on the domain, I guess I should say the antiderivative of the integral. So we've done an operation. The next thing should take on the same domain. However, the natural log function doesn't include all those negative values for the argument. So you have to limit it so that you only have absolute value in there. And that's just to protect you, that you wouldn't go plugging anything in that you were not allowed to plug in. So let's do some math. See how this works. We're going to still use U substitution here, so we're just going to get better and better at that as we go. Example 1, a very basic one. The integral of 1 over 2x dx. Right away, you notice that the derivative of 2x is not in my problem. So it's not quite like this. I don't see the derivative there. So I need maybe to do U substitution just to get my 2 and figure out how that works into my problem. Or what else could you do? I could do U, or I could straight up solve this without U. Take 1/2 to the outside. 1/2 times 1 over x, that's the same thing as 1 over 2x, right? Because it's multiplication. Addition you can't do that with. The multiplication you can. So now you've taken care of the 1/2. You've figured out how that plays into your integral. And now you can straight up say, I know what gives me this derivative. If this is the derivative, I know what the original function is. I'm going to keep, this is an x, by the way. I'm going to keep the 1/2. I'm going to say the natural log absolute value of x, and I'm not going to forget c. So that, taking things out to the front is really helpful because it simplifies your problem. It would have been a little bit more complicated with the u, just more steps that we don't need. This one I can't do the same thing with. So I've got the integral of 1 over 4x minus 1 dx. What would you want to do? Okay, you want to separate when there's only one thing in the bottom. Are you trying to make separate fractions? Okay, so rule is if there's a monomial on the bottom, you can separate it because they have a common denominator. But this, and that's a great point to recognize early on in this process. So this can't be separated because this is an entire unit in the bottom. So only when there's a monomial in the bottom can you separate it. So we can't separate it. Let's think about it like we did with our last section. Let's make the bottom u. Because if I make it 1 over u, I know I can do natural log. So if I say u equals 4x minus 1, it's chain rule, okay? it's going to have some derivative because this has du over dx equals 4. Derivative of 4x minus 1 equals 4 plus 0. And so if I rearrange this guy, I'm going to have du over 4 equals dx. So I haven't written all the rearranging, but are y'all okay with this if I do it in my head? Okay. Which means I can replace it now and say that I've got the integral of 1 over, replace this with u, replace dx with du over 4, which I can just put in the front. Once I start to see that pattern, I can just put it in the front. Now it looks like my last problem. I keep the 1/4, I make this absolute value. I'm going to say that's equal to 1/4 natural log absolute value of u, but I'm not going to write u. I'm going to say 4x minus 1. And when you check it, you would say the derivative of this would be 1/4 times the derivative of natural log is 1 over the argument times 4, these cancel, and I've got the original problem. So I do want you to see, and I do want you to think about checking them so that you have an idea, and then the C would go away, so that's fine. But if you've got time to check it, it's worthwhile to do. It makes it less, I'm just following some random rule that somebody gives me, and oh, I see how that actually works. All right, some of them just bring you joy because they're very straightforward, like this one. She tells you in advance, so you'll be looking for it. Let's look at the integral of 3x squared plus 1 over x cubed plus x dx. So this is my height, this is my width. I'm not forgetting dx because that's how you make area of a rectangle. And so what do you see? The top is the derivative of the bottom. So you can do u substitution and see how it all works out, but there's the rule up here that says if you have the derivative of the bottom, then you can just write the natural log of the bottom. But you may not have pushed that I believe button yet, so let's I believe it. So u equals x cubed plus x du over dx. Charlotte's already said is 3x squared plus 1. Rearrange it, it gives you du over 3x squared plus 1 equals dx. So this goes in the bottom, this goes in the top. And then you can say, okay, what happens? 3x squared plus 1, that's what I'm trying to get rid of by making the bottom u. You want to make the biggest one the one that's u because when you take its derivative, it will be a smaller degree. And then when I replace dx with this fraction, du over 3x squared plus 1, these cancel. And then you have the natural log of the bottom, x cubed plus x plus c. Does that make sense? So if you can visualize that this is the derivative, you can cancel it and then take the natural log of the bottom as long as it's an absolute value. If you see that it's the derivative, because if you check this, it'll be 1 over this times the derivative, which is what you're trying to cancel out. You're always trying to cancel out the chain rule, the extra step. That's what's going to make it more simple. But if it's not exactly the derivative, then you need to do what we did in this problem up here so you can take advantage of any scalar multiple that you need to fix it. All right, so let's see. What am I on for? Okay. Let's do a definite integral. From 0 to 3, those are my limits of integration of x over x squared plus 1 dx. So this would say, find the area between this function, the x-axis, and x equals 0 and x equals 3. So that looks like whatever the function looks like. The vertical line x equals 0, the vertical line x equals 3, and the x-axis. And the equation happens to look like this. So we're looking for this area. So I want you to look at integrals and think area. Because when you're given geometric models and you're actually finding area, those two things will come together. So what do we need to do here? We can't make separate fractions. We've been doing that, and that is the first thing that comes to mind. We can't, though, because we don't have a monomial on the bottom. So the top is almost the derivative of the bottom, but not quite. So if we just do u substitution, we'll get the scalar change to that, right? Okay. So u equals x squared plus 1 du dx equals 2x. So du over 2x equals dx. Oops. Why am I not going to write my 0 and 3 there? Yeah, so if I write u for a second, I don't want to put x values in here. So I'm just going to leave it blank. That's my personal choice. It saves me some work because later I'm going to put it back in x and just work out with those numbers. So anyway, I've got x over u. Instead of dx, I've got du over 2x. So 2's in the bottom. I put it in the front. I'm making a lot of leaps here. Are y'all okay with all that? Okay, cool. So x cancels x. And now I have 1 over u du. So I have 1/2. Oops. Yeah. The natural log of x squared plus 1 evaluated at 0 to 3. So I sort of cheated by not putting anything here. I put it back in terms of x, and then I put my x's back. If I needed to put the u ones in here, I would say 0 in here is 1, and 3 in here is 10. But then I like to change it back to x, because that's how, then I can just do all my math the same way all along. So now which one do I plug in first? The 3 or the 0? The 3. So 1/2. Natural log of 10 minus 1/2 the natural log of 1. Can we simplify any further? I don't need plus c because they would cancel out. So if I'd have had a c, I would have said plus c here and minus c here, and so they would cancel. But always do the consider just to make sure that we don't need a plus c in this problem. But there is something else we can do. What does natural log mean? What are logarithms? They are exponents. What exponent will make e 1? 0. So e to the what power makes this 1? This is the result of e to the 0 power. So this is 0. And I want to remind you of those little math facts in case this was a problem that's not a calculator problem, where the answer is given as 1/2 the natural log of 10. Now maybe you'd like just guess it because you're like so close and you'd be cool with it, but this is 1/2 times 0 because we're looking at e to the what power makes 1. And we can replace this with 0. Okay, you could also see this answer as the natural log of the square root of 10. So don't forget that the numbers in the front are actually exponents. This would be like 10 to the 1/2. you could also see it written like this. So there are multiple ways to get this answer. And because I just dropped these absolute values, because when I started plugging in numbers, I got positive numbers. I didn't need the absolute value of 10. 10 is just 10, okay? So I didn't talk about it. I sort of forgot about it till just now. But when you start plugging in numbers, then you know that that you don't need the absolute value anymore. So how about that? Sometimes the book may say round to 3 decimals, then you know you need to take this and put it in a calculator. But as far as a mathematical answer, this is cool. Like, we're done. We don't necessarily need to go get a numerical answer. We've found an answer. Okay, so definite integrals work the same, and that's good. So up to this point, all of our examples, the top has been a smaller degree than the bottom. Because when we take the derivative, we go down a degree, and so things cancel. So here's where long division comes into play. Example 5. Example 5 says, please take the integral of x squared plus x plus 1 divided by x squared plus 1. So again, it's a rational function. I'm thinking, okay, I can either separate them like I first learned to do with all of my stuff, except this is a binomial, so I can't use that. I could think it's the natural log, and if I take the derivative of the bottom, do I get the top? No. So instead, long division provides us with separate fractions. It's the way to separate them without separating them. So here I go. Long division. X squared plus 1 goes into x squared plus x plus 1. And we're going to find out what the quotient is and the remainder, like we did in Algebra 2 and Precalculus. And then we'll have separate fractions that are simpler that we can use. X squared goes in x squared once, then you multiply x squared plus 1. Change the signs. I've got x. Does x squared go into x? No. It's the remainder. Do you remember how to write the remainder? Yes, so x over x squared plus 1. Just like if you were doing numbers, you'd say, I've got 1 left over, that's 1/5 at the end, or whatever. So now I've got the integral of 1 plus x over x squared plus 1 dx. So we actually did the division. We took it from division to be a quotient, and now we can take the integral separately. So the integral of 1 is x, yeah? And the derivative of this guy, I might need to use substitution. So x over x squared plus 1, just because I'm going to have a 2 somewhere. And you may already be really good at that. I am paranoid that I'll put the 2 in the bottom when it goes in the top, or vice versa. So I pretty much do use substitution every time so that I'll get that constant correct. So if u is x squared plus 1, du dx equals 2x, period. So I'm going to have the 2 in the bottom. I'm going to have du over 2x equals dx. So I'm going to have x over u du x 1/2. We've already done that problem. I'll pause and let you catch up. You could wait and do this derivative or antiderivative of x, all at the same time, but I did it earlier, so I'm not going to forget that. I have x. I have 1/2. The x's cancel. Now I have 1 over u. Make sure you go put that 1 there so that you don't think you're doing u squared over 2. Okay, keep it a fraction looking. So 1/2, and then the natural log of u, which is x squared plus 1 plus c. So if the numerator is a bigger degree than the derivative, you're going to have to do long division. You're still going to have natural log in your problem because the remainder will be a fraction that you can do use substitution with. But you've got to simplify it to the other factors to get there. All right, so do you feel like you have a sense of when to use long division? You've got some practice with it. You'll get it. I know you will. Here's some more fun. Let's do okay, here's an obvious one for you. I don't know what example. Okay, 6. Again, I say obvious. You may not think so, but here we go. Secant squared x over tangent dx. By obvious, I don't want you to rewrite this in sine and cosine and cancel things out. Although you might could. I don't know. But you're looking for u prime over u so that you can say that's the natural log of u. Do you have that? You have the derivative of the bottom on the top. So you can pretty much just like cancel that out and go, that would be what's chain rolled. Now I'm taking the natural log of the bottom, so it's going to be looking weird. Tangent of x is inside the absolute value plus c. And tangent has negative values, right? It looks like this. So we're talking about just using this part. We can't even evaluate this part because it's negative. And then what do you do if we're just looking at, I think there's a homework problem like this, tangent of x dx. So this one's not as straightforward. This one's not something I already know the antiderivative of. It's not in my list of things that would give me something that's tangent. So we can't use this rule. I don't know one already. This is when we go to trig substitution and just straight up sine cosine it and see how that helps us. So what if I say instead this is, which one is it? Which one's on top? Sine of x over cosine of x dx. Oops, a little extra there. Do you see the derivative of one or the other? Okay, you need to consider it to be the derivative of the bottom one because you're going to end up with u. You need the u in the bottom. Otherwise it doesn't cancel the same. So we just add a negative, right? So if we were to do u equals the bottom, we would end up with that negative. So that would take care of it. But you saw it, so you could just add it. It's just the one little thing we have. Du dx would be negative sine x. So when we rearrange this, we'd have to go negative, and then this cancels. See what I mean? Okay. If not, then you go through the whole process and do du over negative sine x equals dx. And then you'd say sine x over u du over negative sine x. Sine cancels, we still have the negative. So go through the process if you need it. There's nothing wrong with that. It really does help with the little details that you need to get right. So then I've got a negative 1 over u du is going to be negative the natural log u I said was cosine, and then I don't need a dx. Instead of dx, that helps you remember to write plus c. So you have, it's just straight up math homework where you're practicing these ideas with still use substitution, using the denominator or long division first so that you can simplify it. And then I think it's mainly odd, so if you really get stuck, you can check with CalcChat and see what they do. So here's the problems that I have for you. So on page 356, 9 through 21 odd, and I can put my book up so you can see it. And then 51 through 57 odd. So it gets you stronger with use substitution. It includes the rules for natural logs and goes back to long division, which you didn't necessarily like in Algebra 2, but by now it's pretty simple. Yes. So I'm going to take a picture of this and add it to Classroom so you'll have it, but I'll leave it up here too. So 351. Let's see, 9 through 21.